What is the point of weird sums like this one? Supposedly, if we add up 1 plus 2 plus 3 and so on, the result is negative and not even a whole number? Some mathematicians have called this one of the most remarkable formulas and one of the best kept secrets in math. But others argue that this is a misleading trick that changes the meaning of equals. So, what is the point of these weird sums? This video is sponsored by Squarespace, an all-in-one solution that makes it easy to build your website and succeed online. Let's build up to this sum starting with a microwave. We can set a microwave to 50% power, which can help heat the food more evenly. But how does the microwave do this? The microwave actually switches from full power to no power back to full power at equal intervals. We can write 1 for full power and 0 for no power. The microwave's behavior looks like this: 1, 0, 1, 0, and so on. This sequence diverges, so how is this 50%? The microwave never actually runs at 50% power, and its behavior doesn't approach any limit either. It just alternates forever. But let's look at the running averages. The first running average is 1, and then the average of 1 and 0 is 1/2. Then we get 2/3, 1/2, 3/5, 1/2, and so on. The running averages aren't always 1/2, but they do converge to 1/2. In the long run, the microwave's average power is 50%. One last step, let's create a series by using this sequence as the partial sums. The terms in the series are like the change that we have to apply to go from one state to the next. So first we have 1, then a -1 to change from on to off, then +1 to change from off to on, and so on. In calculus, this is a famous example of a divergent series. Its partial sums diverge, so it's not summable. But just because a series diverges doesn't mean we can't say anything about it. When we look at the running averages of the partial sums, we see they actually do converge to 1/2. So we say the series is Chizaro-summable to 1/2. This value of 1/2 has real physical meaning, representing that the microwave's average power in the long run is 50%. Similar tools can help with Fourier series. Fourier series give us a nice way to approximate a function with sine and cosine waves. As we add more and more terms, we get better approximations to the function. But something weird happens when we try to approximate a function with a discontinuity, like this square wave. We notice these significant errors around the discontinuities that stick around even as we add more and more terms. This is called the Gibbs phenomena. One way to address this is with an obel sum. The idea is to multiply the terms by a damping factor that's a little less than 1. This smooths out the fluctuations at high frequencies. Abel's theorem tells us that if our original series converges normally, then damping the terms and taking the limit outside the sum as the damping factor approaches 1 from the left will recover that same value. This is called the Abel sum. For a convergent series, we will get the same answer. But sometimes we can apply this technique to a divergent series. The damping factor helps to calm down the terms so it's easier to be convergent. We can take a limit afterwards as the damping factor goes to 1. For example, the series 1 minus 2 plus 3 minus 4 and so on diverges, since the terms don't tend to 0. But this series is actually Abel summable to 1/4. Let's apply this idea to our Fourier series for the square wave. We apply a damping factor to each term in the series, and now we've smoothed out the Gibbs phenomena. Modifying our sum in this way gives us a better approximation around these discontinuities. Just like we needed the right tool to fix our Fourier approximation, if you're building a website, you also need the right tools. I used to work as a software developer for a large e-commerce company, so I can tell you firsthand about the many intricacies of building and maintaining a website. But with Squarespace, all of those technical issues are handled for you. Squarespace's design intelligence combines decades of design experience with powerful AI tools, so you can build a beautiful custom website with no technical skills required. You can even create and sell your own online courses. You can pick your layout, upload videos, and add a paywall. Getting started with Squarespace payments just takes a few clicks, so you can start accepting payments right away. Your customers can pay with many popular methods, including Klarna, direct debit, Apple Pay, and more. Squarespace handles all the technical aspects so you can focus on your content and your audience. Check out squarespace.com to start your free trial today, and once you're ready to launch, go to squarespace.com/Dr. Sean to save 10% off your first purchase of a website or domain. Now, let's talk about the sum 1 plus 2 plus 3 and so on. This sum, of course, diverges to infinity, and in many contexts, that is the only sensible answer. So why would we ever want to assign it a finite value? And why on earth would that finite value be negative 1/12? This series appears when investigating the Casimir effect. Imagine two flat, uncharged conductive plates in a vacuum. The plates are incredibly close together, only a few nanometers apart. Despite being in a vacuum, there's actually an attractive force between the two plates because of quantum fluctuations. At extremely close distances, this attractive force can be as strong as 1 atmosphere of pressure. This force has been measured experimentally, and it matches the predicted calculations. To get an idea why this happens, let's consider a simplified version of the calculation, sometimes called a toy problem, where we work with an idealized one-dimensional setting. In this toy problem, we can scale the energy to end up with the sum 1 plus 2 plus 3 plus 4 and so on. Although the series only appears in a toy version of the Casimir effect, the three-dimensional version will have the same issue, running into a series that diverges to infinity and needing a way to assign that series a finite value. One way to handle this is to view it as a special case of the zeta function. Zeta of s equals the sum of n to the power negative s. When s equals -1, we get back our original series. This zeta function converges when s is greater than 1, and also for complex numbers with real part greater than 1. We'd like to extend this function to the entire complex plane through a method called analytic continuation. As a simple example, say we have the function x squared plus x over x plus 1. This is a nice linear function, except it has a hole in the graph at -1. If we try to plug in x equals -1, we end up with 0 divided by 0, and the function is undefined. But say we want to extend this function to the entire real line. The natural way to extend the function is to fill in the hole, creating a continuous extension. Any other choice we make would create a discontinuity at -1. Analytic continuation is similar, but we want our function to not only be continuous, but also to be expressed as a power series. It turns out there's a unique analytic continuation of the zeta function to the entire complex plane, except there will be a singularity at s equals 1, meaning the function still diverges at that point. It's pretty amazing that there's only one way to do this. The complex plane has a lot of structure, which limits the possibilities. This function is called the Riemann zeta function. If we plot zeta on the real line, we get this graph. We can now plug in s equals -1 and find that the value is -1/12. This method is called zeta function regularization, which gives us a way to assign our divergent series the finite value of -1/12. We can also assign finite values to other divergent series with this method, like the series 1 plus 1 plus 1 and so on corresponds to s equals 0, and plugging s equals 0 into the zeta function gives us -1/2. There are other ways to regularize our series, like using an exponential cutoff function. This is similar to what we saw with the Abel sum, but with more aggressive smoothing. Now, why would we need a regularization like this to calculate the Casimir effect? At high frequencies, metal stops being a good conductor, and the regularization with an exponential cutoff simulates these physical constraints. It's worth noting that the different regularization methods, like zeta function regularization or an exponential cutoff function, yield the same value of -1/12. This may help convince us that it's more the act of regularization that's needed for the calculation, rather than the specifics of whatever method we choose. Since the value is -1/12, the Casimir effect is attractive. So we find that this weird sum, -1/12, isn't arbitrary. It has real physical meaning in the attractive Casimir force between the plates. These alternative summation methods aren't just abstract theory, they help reveal measured quantum effects. So is this sum remarkable and a best-kept secret, or is it just a mathematical trick? Well, certainly zeta function regularization is a very different notion of equals than what we would typically use for infinite series. And this notion is not going to apply to every context. In some contexts, this series just diverges to infinity, and that's really the end of it. But there are physical problems, verified through experimentation, where these regularizations are necessary. And to me, the fact that the value turns out to be -1/12 is nothing short of amazing. Let us know what you think about this series in the comments, and subscribe for more videos like this one. Thanks for watching, and I'll see you next time.